Hello and welcome everybody to today's tech talk on AI robustness. My name is Tobias and I'm a data scientist at Faculty. In Faculty, we have the mission of making AI real, which means that we want to make it accessible, we want to deploy it in the real world, and we want to make it accessible in the fields where it really matters. We have a track record of hundreds of different clients, hundreds of different projects across different sectors of industries and businesses, which really gave us the opportunity to gather that experience to actually deploy AI in the real world. However, AI is a really powerful technology. So we have early on recognized that it would be irresponsible to deploy that many projects without any concern about the safety of this technology. So our research and development department works on research in AI safety, publishes academic research in papers, but also helps to transition this research into deployed projects at Faculty. So I just give you a quick overview of today's talk. I will start with a gentle introduction to AI safety, then move on to some of the questions that people pose themselves in robustness and some of the potential solutions. Then I will go on to Faculty's contribution into AI robustness, which is a framework for credibility of model predictions. And then I will present how this credibility framework can be applied in practice. And I will end the presentation with a little Q&A. So throughout the talk, you'll be able to write your questions whenever they arise into a little Q&A field, which is an icon that you will see below in your screen, hopefully. And I will pick up that question at the end of the talk. All right, let's start. So what are the things that come to mind when we think of AI safety, or the things we worry most about AI safety? Well, certainly it's Terminator and killer robots. But actually the variety of risks is very broad, touching very different aspects in our world, in our society. Due to that large variety, of set of risk, we have generated a way of categorizing these risks according to two axes, which is one, intention, which can be separated into benign and malicious, and secondly, autonomy, which can be separated into human-controlled and autonomous. So the previous examples can be positioned in those quadrants. There's another axis which is kind of parallel to autonomy, which is a time axis, in which says that human-controlled AI development is more a near-term thing, while autonomous decision-making falls more into the long-term regime, which might then also include, all these horrible existential risk scenarios such as killer robots. Here's just a number of different examples that fall into these different quadrants. They can be divided into technical problems, meaning issues that can be solved by technical solutions, such as unsafe reinforcement learning, meaning that it's likely to make an unsafe reinforcement learning algorithm safe by improving the algorithm, meaning that making a goal safe or making sure that every action taken is safe. There's the other class of risks which fall into policy problems. So those are problems that cannot solve by any technical advances. An example of this is mass unemployment. So if we consider a robot or a machine that has been created to do work that otherwise would have been done by a human, any technical advance on this machine or this robot will not make it not do that work anymore, because that will just defeat its purpose. So an intervention needs to come from politics and broader society. Among the different examples that we've seen, faculty has identified 4 different areas of AI safety on which we concentrate, which fall all into the lower left quadrant, which meaning benign intention, because we assume that most AI development is intentionally benign, and human control, just because we believe that the near-term development of AI will have the biggest influence on the current world. So we specifically, we consider these 4 different aspects of AI safety, which is fairness, privacy, explainability, and robustness, which is the topic of today's talk, where we ask ourselves questions as, is my model robust in the real world? Can I estimate uncertainty? Does it generalize well? Is it robust to things like cyber attacks? And will it still give useful predictions even if my data changes over time, say? So let's just discuss some of the questions that people have posed themselves in robustness and some of the solutions of this. Well, overfitting is a quite well-known problem. Here we see data that has a linear relationship and a highly nonlinear model that fits the underlying training data perfectly, however, performs pretty badly on an unseen data point. Now, this graph might seem a little bit ridiculous, but it helps to understand how a model can seem to fit the data really well, but fails on generalizing. So if we move to higher dimensions, these problems become a little bit more complicated. Well, we can apply things like cross-validation to validate our model during training, such that we can avoid overfitting. However, due to the large dimensionality of those data sets or models, small perturbations to the data can actually lead to a completely different outputs. So here are just 5 different AI models deployed on 5 different data sets, which have on the original test data set very decent accuracy, most of them over 90%, and which is displayed by this coral bar, and then displayed by the gray bar is the performance on the same data set applied with very, very slight modifications. And slight means here, in terms of if the underlying data are images, for example, these are changes that would not be visible by a human eye. However, as we see, is that such small modifications can make my model lose all its utility and all its predictive power. This might make you think that such examples are edge cases and are like manually constructed changes in my data, but data can also change in a very natural way over time, and thereby make our model lose its predictive power. For instance, if my model has learned correlation, which doesn't capture the underlying cause of a dynamic. So as an example, in 2011, until 2011, the Bitcoin price was very, very closely correlated with public awareness. So public awareness and Bitcoin price increased in very similar ways until the Bitcoin price crashed in 2011, which break that correlation. And now, of course, any model that makes its price prediction based on the correlation on public fairness also breaks, in the sense of it loses its predictive power. A more robust model would have learned the underlying causality of the dynamics. So these were just a few examples and issues that people are confronted with in AI robustness. Here are some approaches. They're by no means they are a comprehensive list of approaches, but just to give you a little glimpse, there is data sanitization, which means that even before I start training my model, I clean my data of malicious content, which in practice means I might have to train a second AI model, which just serves as a filter, or I have to employ a human. There's the field of robust learning, which means that I redesign learning procedures in such a way that it has identified malicious content and has made exceptions for this one. There's some strategies in statistical methodologies such as regularization and inference that can be applied. And of course, there's a race between attackers and defenders of AI, where the defenders always try to be on top of malicious content that is out there, and the attackers, they want to create more and more new and unknown malicious content. Of course, another approach is a thorough testing, meaning that we don't only look at the kind of usual case of my data, common cases of my data, but the edge cases, the cases where my data might be slightly corrupted or has slightly a noisy input. And then there's the field of formal verification. This is a framework which tries to achieve that malicious content will never be classified as benign. Well, of course, this is closely related to robust learning, by the way. Well, of course, we don't have access to all malicious content. So what people do in practice, and this is a common practice in malware detection, is that slight modifications of existing malware is also classified as malware. So this is just a little overview on how to deal with problems in robustness. And from this, I'd like to move on to faculty's contribution to AI robustness and to a problem that we have not yet considered in the previous examples, which is the problem that AI can be wrong and AI can be at the same time very confident that it is right. So as an example, we have here an image of some fish, which the model predicts as a frog, which can be explained by the model seeing the eyes of the frog as the fish. Or another example where AI just gives out rubbish because it just has to make a prediction for whatever data we give it, even if the data doesn't have any content. But the problem here is not only is the model wrong, but it's very, very confident that it's right. So the aim of our work on credibility at faculty is to know when AI doesn't know. Or more formally speaking, we want to develop confidence intervals for predictions which are based on sound statistical methodology and which work across a range of different models and data sets and give out meaningful results which can help us to make our models more robust. So I will explain this credibility approach along one example throughout this talk. So I will just quickly introduce this example. It's about predicting someone's income. The data is census data from the US in the year 1996. Attributes contained in the data are information on occupation, education, marital status, and so on. And the target is to predict whether a person earns more than 50,000 a year or not. So the original model that we applied here is a multi-layer perceptron, which achieves 85% accuracy, which is more or less state of the art for this problem. It is a very well-known data set and a very well-known problem, which is accessible in most, in a lot of places online, and it serves as a predictive or can be used as a predictive model for credit risk. So let's see. Let's have a look how this idea looks in practice. So we have a new unseen data point, say a doctor or a nurse, and my model makes a prediction, say this person earns more than 50,000. And my question is, can I trust this prediction? So one thing one could do is to look at similar predictions from the past on data points for which I know the labels, and see whether the model did well or not. Well, in this case, I could consider a bunch of different medical workers, look at their predictions, and see how many of those were correct. But in this case, all of them were predicted earning more than 50K, but most of those predictions were wrong. So I might question whether the original prediction on my unseen data point is actually correct. But the real question here is, what does similar mean? So similarity between data points might not be just identified by occupation. That might not be the right thing to do. After all, occupation is just one attribute among a large list of attributes in our data. So what we need is a meaningful way of measuring similarity between data points. In practice, how we achieve that is we employ a variational autoencoder, which learns abstract representations of our data in some encoded space. And every point in the encoded space corresponds to an original data point. And similarity between data points can be measured by the distance between the points. So just a quick note on how this encoding works on a more from a more technical point of view. So basically my encoder is just a neural network that is trained on my original input data, which is high dimensional, which has all these different features. Some of them continuous, some of them have discrete classes. And my output is an encoded representation, which is low dimensional, where every point is actually a probability function, which is Gaussian, hence identified by its mean and variance, a space that is continuous, and a space where I can define distances between points. So important here is that my loss function with respect to which the weights in my neural network are optimized has two parts. One is a reconstruction loss, which makes sure that data points with different, which are different, are classified in different regimes of my latent space. And there is a regularization term which tries to make the latent representation a smooth space, meaning getting rid of gaps. So how this looks in practice, let's consider this slide. Here we apply a variational autoencoder, or the encoding bit of a variational autoencoder for a data set with 10 different classes. On the left-hand side, we see what happens if we train our encoder, our neural network, only on the reconstruction loss. We see that data which belongs to different classes is well separated. However, there's kind of large gaps between different parts of the data, meaning that if I have a point in this gap regime and I was going to look for similar points, then I would have a hard time to find any other point. So in the middle, we see a plot where we optimize just with respect to the regularization. What we see here is just random samples from a uniform Gaussian. And then on the right-hand side, we see what happens if we combine both approaches together. So we see that different points of different classes are still separated geographically in different regions. However, regions are more close together, and we have a continuous space. In that respect, also note the different scales of the axis between the first and the second graph. All right, so let's employ this encoder on the data set that we have at hand. So this plot displays the latent representation of my data set in a two-dimensional latent representation. One thing we immediately observe is that the two salary groups, the two label groups, are kind of visually separated in this latent space between north and south. We can also compare the latent representation of my data points with respect to salary to other attributes such as sex. In this case, we observe that among the high earners, among the earners of more than 50,000 K, there's more men than women, which makes us see a clear gender gap in this data set. We can compare to marital status, which is interesting from two different points of views. One is that we see a quite smooth transition between intuitively very different values of marital status. So we have never married on the top and married on the bottom, which are very far from each other. And in between, we have a smooth transition from never married, divorced, separated, where divorced and separated overlays almost completely, which tells us that, well, this representation of our data definitely has some meaning. And the second aspect of why this is interesting is that we can see that most of the more than 50K earners are married, and most of the never married people in this data set earn less than 50,000. So a last example is to look at age across my data set in latent representation. And we see that, well, most people earning more than 50K are either middle-aged or a little bit older, while as a very young adult, say at beginning of 20s, it's very unlikely that you earn more than 50,000 a year. But let's take a step back and think about what we've achieved so far. So we have found a meaningful representation of our data in some latent space, which is now nice and neat, meaning it's low dimensional, it's continuous, and I know how to measure similarity between points, which is what we initially wanted to do. So let's apply this framework to our initial idea to evaluate the credibility of an unseen data point on already seen data points that are similar. So this relates to credibility in practice. So let's consider this. We have an unseen new data point. Let's call it Hans. And there is many other data points that are similar to Hans. Most of them have been incorrectly classified. So we should be wary of trusting the prediction we receive for Hans. Another example here is Captain America. Well, Captain America is quite unique. There's very few people that are similar to Captain America. Among those people, the corrections have all been correct. However, since there's just very few of those, we shouldn't be sure that our prediction for Captain America is correct. In the last scenario, we consider Else. There's many, many similar people to Else. And among those people, the model almost always predicted correctly. Hence, it is likely that my prediction for Else is also correct. All right. So what we consider here is the credibility score, which we have now introduced, so a way of computing a credibility score based on similarity of previous predictions, and how this credibility score looks on top of the data points in our latent space compared with the correctness of predictions in our latent space. And we see that there's clear, strong correlation between credibility and correctness of predictions. We see that towards the top, there is a high credibility and a good chance of my model to be right. And towards the bottom, there's lower credibility and higher chances of my model to be not right. But also there's very clear local correlations that go beyond this kind of more general observation. So we can go further and say we divide our data set in 4 equally sized subsets of increasing credibility. So the lowest quartile would contain all data points, the 25% of the data set with lowest credibility. What we observe here is that the higher the credibility, the higher the chance of earning less than 50,000, which suggests that it is easier to predict with certainty that somebody earns less than 50,000 than somebody that earns more than 50,000. We can consider 2 of those credibility quartiles, namely the lowest and highest, with respect to what a marital status values those have. We see that in the low credibility region, most are married, and in the high credibility region, most are never married. But if we think back to one of the previous plots in which we have seen that among the never married people, almost all of them earn less than 50,000, it kind of explains why here in the high credibility quartile, which comprises almost only never married people, the model can be quite certain about its prediction being less than 50,000. For married people, it is more difficult. We can introduce and apply another aspect of AI safety to this scenario, which is global Shapley value, which is basically a framework of measuring feature importance, or more precisely, it measures how much accuracy the existence of a particular feature adds to the overall accuracy of a model. We see that for the high credibility quartile, the only thing that I have to know is the marital status. Again, we have seen that among those in the highest quartile are only never married people, which always earn most of the time earn less than 50,000. So this is basically all my model needs to know and then make that prediction. While in the lowest quartile, there is kind of a bunch of different indicators that are relevant, which seem quite usual indicators, such as education, occupation, and so on. We can sum over global Shapley values, meaning that sum over the different global Shapley values for different features, which is a measure for the overall accuracy of our model. So a higher sum of global Shapley values means a higher accuracy. What we see here is the higher the accuracy, or the higher the credibility, the higher the accuracy. So that's just another further sanity check for our credibility framework. Okay, let's take again a step back and think about what we have achieved so far. Well, we have found a meaningful way of measuring credibility for model predictions for certain unseen data points. It is meaningful because it correlates with the correctness of predictions. Higher credibility means higher accuracy. And we have seen that we can use this framework to actually understand our model better. But what about the confidence intervals of predictions, which were our initial goals, which correlates with the question, with the goal of knowing when AI doesn't know? this graph compares our credibility score with average test accuracy among all data points with a particular credibility score. So since this model is quite a good model, there's quite few data points with small credibility. That is explained in the large error bars on the left-hand side of the plot. These corresponds to the regions where I don't necessarily want to trust my model. Again, since it's a good model, there's fairly many data points in the high credibility regime for which I receive small error bars on my model accuracy and a high model accuracy, which are the regions where I want to trust my model. But we can even go further than that. We can look at different subsets of our data points with highest credibility. So this plot shows model accuracy for different proportions of my underlying data of highest credibility. If I consider all of my data, which is 100% of data, I just end up with the baseline model accuracy of 85%. All right, however, for the 75% or a little bit more of data with highest credibility, I receive an overall accuracy of 90%. And I can even go further and say that for 50 or maybe 55% of my data with highest credibility, I achieve an accuracy of even 95%. So how could we use that in practice? Well, if there is a desired or necessary minimum accuracy of, well, let's say in this case, 95%, one thing that I could do is I could evaluate my credibility on my data set, divide it into high credibility, in this case, 50 or 55% of my data set, and low credibility, meaning the rest. The high credibility set I can just give to my model and let it automatically evaluate, and I receive my desired 95% accuracy. And for the rest of the data, I could either give it to a human, which supposedly has a higher, can employ a high accuracy as well, or give to another model, which is more tailored to the problem at hand. So just to give a quick summary, we addressed some different issues in AI robustness. We talked about some of the questions that arise and potential solutions. We discussed how variational autoencoders can be used to represent data in a suitable low-dimensional state space, and which makes it possible to measure similarity between points. We introduced a framework for measuring trustworthiness of predictions, and which also helps us to understand our model better. We applied this framework of credibility to a real-world data set. Most importantly, this means that we developed a principled way of knowing when to trust AI. And so the latter is also the largest impact of this work, which is the ability to decide when to trust your model. It can be applied as a principled way of prioritizing for human interventions. And the most likely and impactful applications of this approach is going to be in finance, healthcare, cybersecurity, or other kind of high-stake applications. So that was it for now. Thank you so much for your attention so far. And now we definitely have some time for Q&A. I'm just going to read through the questions that have been posed, and I'm trying to answer them one after the other or in what way seems suitable. Just give me a minute to read through them. All right. I have mostly gone through the questions now. Sorry for the wait. I will try and answer them as good as I can. So question number one is, how sensitive is credibility to the encoding? Do you know if different encodings do not give very different results or confidence intervals? That's a good question. In the experiments that we've performed, retraining and learning new encodings does not substantially change the score. Having said that, we have not yet quantified this. We only have qualitative results, so this is something we will be working on. So I would just move on to the next question. How do you account for interdependence between features? For example, most never married people are also very young. Okay, so so this is kind of covered by the fact that we're using a variational autoencoder for generating the latent space representations. It is able to capture correlations between features, and hence those correlations are captured in the latent space. So that covers correlation between different attributes and different features in the data set. What are the main hyperparameters behind the credibility score? I'd imagine the distance threshold under which you consider a point similar is quite key. How do results vary based on that? Yes, if the threshold is too strict, then there's basically no test point that has similar data points, and nothing is viewed as credible because we don't find any data point in the similarity region. But if you are too loose, then I mean, the extreme case would be is that your similarity region would be infinity. You just end up with all points, and all points become equally credible. And that won't be any useful information. Let me just, oops. Just give me a sec. Okay, what are global Shapley values? Does faculty use a proprietary technique for explainability? Well, global Shapley values are a framework that is based on Shapley values, which is an approach from economic and game theory, which basically measures how much accuracy due to the existence of a particular feature is added to the overall accuracy of my model. The problem we encounter there often is that or in more simple words, is they explain models by attributing model performance to individual features, and to the question of proprietary techniques. No, it's not proprietary, sorry, but we have made several improvements. Could we review the definition of credibility and how it is measured? certainly there's some of the aspects of the definition of credibility that have not been exposed in this talk. So there's for sure different ways of implementing credibility. So the basic assumption, the basic approach that we follow here is a Bayesian approach. So when we think back of the second example of the prediction of my unseen Captain America data point, that I have similar data for which the model predictions were correct. However, the amount of data I had was very little. That means that I do not necessarily want to assign a high, I definitely do not want to assign a high credibility score on that, but I also don't necessarily want to assign a very low credibility score. So what I basically want to do is having something like a uniform distribution between credibility 0 and 1 with a slight tendency towards 1. And in that case, we have, speaking of this Bayesian framework, we have employed a uniform prior, but of course this is like subject to a lot of discussion. What is the best prior to employ, which is the general kind of general debate in Bayesian statistics. So I hope I more or less answered this question. Your method involves comparing a data point to its neighboring data points in terms of where the prediction is correct or not. How do you determine the size of the neighborhood to check? Well, I hope I kind of addressed that in one of the previous questions. So if you would choose your epsilon neighborhood too little, you wouldn't find any similar data point, you wouldn't have any data, and you wouldn't be able, you would basically assign low credibility to all data points, while if your epsilon is way too big, then you wouldn't get any meaningful information out of your credibility score, because all would have same credibility. So the heuristics that we were applying to choose the radius of the epsilon neighborhood, by the way, this obviously depends also on the dimensionality of the latent representation. So an epsilon of 1 means something very different in dimension 2 compared to dimension 10. So just another point to these heuristics. One thing that we applied was, if I remember correctly, that we choose the epsilon such that something like 99% of the data points have at least 10 points in their neighborhood or so. Apart from the epsilon neighborhood formulation, one could also think of applying k-nearest neighbors. So in that case, you wouldn't have to worry about like finding a neighbor. If you say the 10 nearest neighbors, you always find 10 nearest points. However, those points can be pretty far away in the worst case. Could you go back to the slide that defined credibility? Was it defined as the distance between features encoded in a latent space? Yeah, let's try and go back. Maybe this one is most useful, I suppose. So to answer your question, is defined as a distance between features? No, it just uses the distance between points in the latent space to determine what similarity means between those points. And then it uses the model accuracy on those similar points to determine the credibility of the unseen point. Can you please describe how you derive the CI graph? So there's a few ones with credibility. Okay, this is a tiny little bit technical. It's a tiny little bit involved. I have mentioned earlier on that credibility for a single point is actually not quite just a value, but it's a probability density. If I have a lot of data points and most of them were correctly classified in my neighborhood, then I will end up with a distribution that is skewed towards 1, which means high credibility. So what I do to generate this graph is I sample from this credibility density. Means that for each unseen data point, I have one probability distribution. I sample a number of times of those, and I end up with a bunch of different credibility scores. Now, I can validate my credibility score, which is happening. What is happening here by checking how the model did on this unseen data point. So for each of those samples of credibility score, if they are in the test set, I can, through considering the test labels, see if they were correctly classified or incorrectly classified. So what I can do is I can look at different bins of different credibility. So it's a credibility bin from 0.5 to 0.6 contains 1,000 different instances. And let's say 70% of them have been correctly classified, which gives us the mean value of this test accuracy. And since these data points give us not only like a mean value, but also a distribution over the test accuracy, we end up with these blue confidence intervals. I know this is a little bit involved. I'd be happy to also meet like after the presentation or talk about this on email in a bit more detail. Have you estimated how sensitive are the credibility results to the specific metrics you use to measure distances? So the variational autoencoder imposes a Gaussian prior on the encoded space. So the Euclidean distance is the most nearby, the most principled way of doing it, but there would be also, yeah, there's the possibility of considering different metrics. We haven't done that much. However, one thing that we considered is apart from this credibility score, which is defined by the kind of ratio of correct classifications in a neighborhood, is that I have to think about that again. I'm not sure. There's a few other metrics of you know, kind of other candidates for the credibility score, which never made it to the credibility score. But I would have to review that work again. But I'm happy to answer that separately in an email. In calculating the credibility, you compare to labeled data points in the neighborhood of a prediction. are these labeled data points from a test set or from a training set? It's actually a holdout set. So it's a kind of validation set. So it's neither the testing set nor the training set. So yeah. Could you weight the other points based on inverse distance rather than apply a strict threshold? Yes, I think that would be possible, or employing a weight that decays exponentially with the distance. That's definitely possible, but that's something that we haven't considered yet. Regarding supervised training, in real-world datasets, are labels readily available, or does your team have to work on creating a sample with labels? How is this issue handled with extremely large client datasets without labels? Yeah, I think the only models that we have considered so far fall into the supervised learning regime, so we have actually access to labels. As you say, in real world problems, we don't have them always available, and that's kind of a general problem, I guess, for supervised learning. There are some strategies for obtaining labels without manually labeling your entire data set. Some of those examples are semi-supervised learning or fuzzy labels with some manually specified heuristics. I think that covered. I hope I have covered all of the questions being asked here. We're also good in time. So I'd like to thank you again for your attention and interest and all your questions. That was really, really interesting and engaging. And if you have any more questions, please write me an email and I will try and follow up very soon. Thank you.